4 methodology is available only in TerraChem, but this is very, I'd say, rudimentary implementation that was done about 4 years ago for testing purposes mostly. Right, with these methods, energy and gradient can be calculated. Also, the relaxed density matrix for both states, for the ground and for the excited state, can be calculated. And ionization potentials and electron affinities are also available. They are not available as the orbital energies, so don't look at the orbital energies, they are wrong. But they are calculated via extended Kopman's theorem, and they are printed in the end of the file. We shall do probably a few calculations illustrating this and shall see where you can find it. So typical workflow is, as usual, SCF routine starts from certain initial guess for the orbitals, and guess is really a tricky issue with REKS because you first need to set up proper initial guess. Default guess in games is totally crap and it doesn't work. You need to run ordinary DFT calculation first and then pick up the eigenvectors and insert them into the input file. Right, then SCF cycles follow when they are converged, if requested, of course. If you request gradient or extended Kopman's theorem or relaxed density matrix, then there will be coupled p-tubed REKS equations solved. After that, the further calculations pertaining to the gradient calculation or the EKT, they will follow. So basically, you start from proper input guess, initial guess, then do SCF cycles, and then everything else will follow. Now, the input file for games, if you are familiar with the program, you can easily recognize the new keywords. I highlighted them in yellow. So new keyword is SCF type REKS. That will request REKS type calculations. The other keywords in the control section are exactly the same as in the usual games. And if you request REKS, then it's good to add one extra input block, input section with REKS keywords. Of course, there will be some default values for these keywords, but better to do all settings by yourself and not let program to pick up some default parameters. I briefly explain what all these keywords mean. So first, you request type, REKS type, admissible values of type of the calculation. REKS type of the calculations are 0, 1, 2. And respectively, if you set 0, it will be state averaged REKS. If you set it to 1, then it will be state interaction state average REKS with 2 active space. And if you set it to 2, then it will be SSR 3-2. So 3 state interaction and 2 state averaging. I explained that this methodology, not yesterday, but day before yesterday. So what was Tuesday? Yeah, in the second lecture, I explained about this methodology, that it's similar to SSR 2-2, but adds to the state interaction one extra state, doubly excited state, which may become important in some situations for this description of symmetry breaking and charge transfer systems. Right, so this keyword sets type of the calculation, either this, that, or that. Then target state. If you perform one of these calculations, of course, the program will print only results for one state which you want to study, either ground state or excited state. So 1 or 2. This keyword can take two values at the moment, 1, 2, either S0 or S1. The next keyword is Wpps. This is weighting factor of the perfectly spin paired state in the state averaged REKS ensemble. Default value is 0.5, but you can vary it towards 1. I would not recommend to set values smaller than 1/2, because in this case, the weight of the excited state will be greater than the weight of the ground state. And this kind of inverse situation, my experience shows that it converges very slowly, poorly, and may lead to various problems. But between 0.5 and 1, you can use, you can choose any. Equi-ensemble of PPS and OSS states is all right. So this is default setting. But if you set it, this parameter, this keyword, to 1 exactly, then the program will perform single state REKS calculation, not state average, but single state REKS calculation for the ground state, of course.
So by default, by default, you prefer state average.
Yeah, 1/2, 1/2. Yes, that's a default state average. Yes.
Because even the first keyword REKS type equal to 0, even already state average.
Yes, it's already state average, but if you set it to 0 or to any other value, and then this factor you set to 1, then it will perform single state REKS calculation anyway, not state average, because in this case, the weight of the open shell singlet configuration will be 0 strictly, and it won't make any sense to handle this configuration during the calculation. Right, a few more keywords define some parameters for the ACF cycles, such as REKS shift. This is level shift. I use it to stabilize ACF convergence. So the reasonable values are between 0.2, 0.5. Sometimes you need to select somewhat greater value, closer to 1 atomic unit. It's given in the atomic units, of course. And what it does, it shifts upwards the energy levels of the virtual orbitals, such that it slows down the convergence, overall convergence, so orbital rotations become slower. But at the same time, it stabilizes the process of convergence. Sometimes you may experience oscillatory convergence, so the energy goes up and down, oscillating. And in situations like that, level shift may help to stabilize the convergence and avoid the energy oscillations during the ACF cycles. All right. So DIS.
Excuse me, let me ask again about REKS keyword. REKS type, it's SSR, means orbitals, number of orbitals, 2 and 2, 3 and 2.
No, it's not number of orbitals. It's simply number of, say, REKS methods as they are implemented. 0 corresponds to SA REKS, 1 corresponds to this method, 2 corresponds to that method.
Okay, it's different. Okay, REKS target, that means
target,
conical intersection.
1 corresponds to the ground state, 2 corresponds to S1 state.
I guess
1. Okay. Just you calculate to ground state or excited state.
Yeah, right.
Just only first state or any kind of excited state.
Yes,
first,
right.
Is it possible
to
second? Okay. If you take 3, that means
3 is not defined. 3 is not defined there. So I think that program should print error and abort the execution.
Okay. Do you calculate only lowest excited state?
I calculate, well, if the method includes 3 states, like this method in the state interaction includes 3 states, energies for all 3 will be printed. However, the density, I mean, the relaxed density further and the gradients are calculated only for these 2.
You should choose number of excited state from where is DFT?
It's not number of excited states. Number of excited states in these methods is more or less fixed. It's what
fixed. Okay.
Target
I don't
state.
see. Okay.
Because it does not print information and does not calculate information for all states. It calculates information only for one state which you target, your target state.
How I can choose? How I can choose one of excited state? I need, for example, second. Sometimes second excited state or third excited state.
It won't be second excited state. It's only first excited state.
Only first. That's my question. Just only first. Okay.
Yeah, it calculates either ground state.
Michael, you better tell us the parenthesis 2, the meaning of 2, so that will be for him to understand that easier. 2 means that you can only calculate 2 states.
This means, yes, I include 2 states into the state interaction, and I use 2 states in the state averaging.
So first 2 means what? I forgot. There are 2 numbers, 2, 2.
Yes. First means a state interaction, how many states are included in state interaction, and the other 2 means how many states are included into the state averaging in this SA REKS.
So then, which means that usually 2, right? It should not be 2, 1 or.
Yes, it's 2. Yeah, you don't set explicitly the name of the method. You only tell the program what type of calculation you want to do, 0, 1, or 2.
Yeah, so Vladimir's question was that whether he needs even higher states.
Higher states are not available in the current
you can only calculate 2 states.
Okay, that
so
means
he has a 4, which gives 4 states, right?
More than 4 gives you 10 states.
Oh, okay. So yeah, go ahead.
That means that when we say about, for example, conical intersection only between ground state and first excited state, not between 2 excited states.
No.
Not as it was. Okay. It's pity.
It's like think about. It's like it's like CASA-CF. Okay.
Yes.
You put the active space to 2, then you only calculate 2 states. If you increase 4, 10 states, you can calculate. And we need to implement that 4. For 10 states, it's kind of sufficient for most of the cases. So this is, again, an advantage and this advantage. So if you need more and a lot more, then you need MRSF. The other theory we have. MRSF gives you all states. So, but then you don't have this kind of state average, and we don't have relaxed orbitals for particular states. So test yourself. Okay, so one method gives you all states, but the other method doesn't give you all, but it's a more, I would say, it has a much, you can optimize orbitals. So barational. The other one is barational, but MRSF is non-barational, but gives you all states. So you check it yourself.
We will see later. Yes.
By analogy with CAST-SCF, you can tell that REKS is similar to state-averaged CAST-SCF.
Yeah.
Where you include only limited number of states. MRSF and other response methodologies, they are more similar to CI, configurational interaction, where you can request as many excited states as you like.
Yes, just it's restricted by number of square matrix.
Yeah.
Right.
Okay,
right.
so thank you.
So regarding the ACF convergence, level shift is one of the acceptable ways of stabilizing SCF convergence. And DIS, I try to implement DIS in its simplest form, commutator form. It doesn't always work with REKS. So I do not recommend it to use this accelerator, SCF acceleration engine. We shall work on this on DIS, but in principle DIS is available. You can request DIS setting this keyword to yes. If it's yes, then it will do DIS. If it's no, then it won't do DIS.
But you can do full DIS using the entire Fock matrices.
Yes, I do. This is commutator DIS. And in my experience, previous experience also, this original PULAI DIS does not work well for REKS. Sometimes it does, sometimes it doesn't. The best accelerator for SCF cycles, from my past experience, was energy-based DIS by Scuderia and others. But it is not implemented in games, so I couldn't use it.
Oh, by the way, is this as a direct SCF? You do direct SCF?
It's not direct SCF. It's not direct SCF.
I see. So you save the integral, the hard disk. Then.
Yes, they are saved to hard drive, and
I think it would be nice to do the direct SCF. Then.
Yes, certainly, but it was not somehow in the beginning when Kohn implemented the SCF, SCF cycles. He didn't implement direct SCF.
Yeah. That is something that
I simply carried on using his initial implementation, and then I implemented couple PTUs and everything.
Yeah, it's not that difficult. We are the Fock space.
Well, it's definitely it's not too difficult, but it's
but it needs to spend time, right?
games or to invest effort in another program.
Sure, yeah, that's not easy.
So that's the choice. But anyway, disk-based SCF works reasonably, and everything is all right. At least we have some implementation that is working and can be used for benchmarking other implementations. All right, some few more keywords which may be interesting besides these SCF cycles, which define SCF cycles. There are also these two keywords which request, the first requests extended Kopman's theorem computation. By default, if you set yes, that REKS EKT, it will calculate only ionization potentials. All right. If you set also extra keyword EKT EA, EA here stands for electron affinities. If you set it to yes, its default value no. Then with this combination of two keywords, it will calculate only electron affinities. So it's one of them, either or. So either IP or EA, not both of them together, because the two calculations slightly differ. And I was too lazy to put them into one package. All right, so if you want IPs, you run one calculation. If you want electron affinities, you need another. You run another calculation. So that's how it is at the moment. So input file. There are more keywords. They can be looked up.
Michael, sorry to interrupt you, but you need to tell them that this IP and EP can be also calculated for the excited state.
I can barely hear you. Can you repeat, please? Connection is unstable.
Okay, so IP and EP you implemented is also it can be calculated for ground and excited state both. Oh, you're not hearing me?
I don't hear. It's
Okay, okay.
Always interrupting, stumbling, so that network problem apparently.
Okay, let me change it. Can you hear me now?
Right now, no.
Oh, no?
I
Yeah,
hear
now,
everybody
yes.
very well. I hear,
Ah, right.
Can you hear?
but
Can
in
you hear?
my home network works.
Okay.
Yeah,
Okay. Let
probably
me.
we have some connection problem at work. So that's
Okay.
all right.
Okay. I'm gonna text you. Please tell us that I'm.
So
Yeah, I just text everybody.
yes, they are available for both, for ground and excited states, of course. That ionization potentials and electron affinities are available for both, for ground and for excited states. So these are keywords in the REKS block of the input file. And what is, I told you before that you need to read the initial guess for the SCF cycles. For example, from previous calculation, either standard Kohn-Sham calculation or previous REKS calculation, which has converged. Game's default guess is just a simple Hückel guess, or even worse than that. So it's total crap. It doesn't work. So, and we will later do calculations for one molecule, which is known as TME, tetramethylene ethane molecule, diradical. This is diradical. And for this molecule, the number of molecular orbitals with this basis set, which is 631G star, basis set is 106 molecular orbitals. So that's why I gave this number. But if you calculate another system, another molecule, you need to look what the number of orbitals is and put here proper number. Right, but this I advise you to use if you want to do REKS calculation. Right, about today's simple computation work, we will calculate tetramethylene ethane diradical. It has singlet ground state, but it's strongly correlated multi-reference ground state. So for example, if you try to draw Lewis structures for this molecule, you cannot draw closed shell Lewis structure. They all will come out as diradicals with dots here, there, other way around. So there will be many permutations of the dot centers or radical center. So this is an open shell molecule. Here I show frontier orbitals, and we shall calculate planar and orthogonal conformations. So planar is obvious, and orthogonal is 90 degrees torsion about these bonds, central CC bond. So all atoms are carbons except these hydrogens, right? And about this molecule, for a long time there was some controversy as regards its ground state, whether it's triplet or singlet. As a matter of fact, they are very close, triplet and singlet, at some torsion angle. They even cross or approach each other very closely. So population can be transferred back and forth in principle. Right, but singlet is a global energy minimum and triplet is only a metastable state. So red is triplet here and blue is singlet. So that I copied from one of the previous works. And dashed line shows CAS-PT2 calculations, which do not display any say crossing or near crossing between singlet and triplet. And these asterisks, red and blue, red for triplet and blue for the singlet, they display quantum Monte Carlo results from 2013, sorry. All right. The rest is only, let's say, explanations about the electronic structure and about the pi-type orbitals of these diradical. So you can view this diradical as a dimer of two allele radicals. That would be allele, and that would be allele radical as well. So like that. And they are connected through their central carbon atoms. And this molecule is diradical. So the pi-type molecular orbitals can be built using molecular orbitals of allele radical, B2, A2, and B2 again. So the symmetry in C2V group. And it's more convenient because we may consider intermediate torsion angle, not exactly 0 and 90 degrees, where it would be D2H and D2D symmetries, but also intermediate torsion angle. So therefore, D2 symmetry is more convenient to classify the orbitals. And in D2 symmetry, these two orbitals, B1 and A type, they are the frontier orbitals of TME, tetramethylene ethane. All right, what shall we do is listed here. So first we shall do single reference Kohn-Sham calculation to set up the geometry, make input file, and so on. And then we use molecular orbitals from these single reference Kohn-Sham calculations to start a REKS-22 calculation, state average calculation. We shall use the same geometry, and we shall read eigenvectors from the previous calculation. I show you how to do that with games. It's not automatically, it's not done automatically. It's a very inconvenient program, not like Gaussian, for example. All right, and then we shall do state interaction, state average. In fact, we shall do this calculation because they are not really different. And we shall try to optimize the geometry. Right, this is, okay, some further explanations about the molecule, if it's interesting. So for planar molecule, B1 orbital and A orbital, they are populated like that. So B1 is stronger populated than A. But for our 90 degrees orthogonal conformation, A orbital is slightly stronger populated than B. So that was from my previous calculations, and we shall see how it works with you. All right, let's